Okay, so I'm finally back from my 2 week moratorium, and today I'm going to finish the tangent line saga, at least for the time being. Today we're going to go over the polar tangent lines. Now, this is a way to find the slope at a point, or a representation of a slope at a point of a polar curve, meaning a curve on a polar plane being um, a plane in which any point can be modeled as a distance and an angle from the origin. Okay, so first I'd like to apologize for the horrible notation. I seen over here, I had to create this in a Google slide, and so it all looks pretty bad. But nonetheless, today we're going to go over polar tangent lines, as I've already stated. As all tangent lines, it's going to be represented in the form y minus a equals mx minus b, also known as standard format. Now, what's odd about polar is despite the fact that you're going to be given a equation in polar form, and despite the fact that you're going to be given a polar coordinate, you have to write your tangent line in parametric form, meaning xy. X and y both being represented by separate equations. That's why this is a parametric coordinate rather than a rectangular one. Okay, so when trying to find a polar tangent line, as I said, you have to first convert your variables into in terms of x and y. X is equal to r cosine theta, meaning the r theta being the equation for just a polar curve. So you multiply that by x as well as cosine theta. Y is r sine theta. So that's how you convert your polar points into rectangular or parametric points. And in fact, the slope, or I should say the derivative of drd, the derivative of r with respect to theta, drd theta, is equal to dy over d theta over dx over d theta. And what this means is that in order to find the derivative of r, the derivative of the polar curve, which you're going to have to do since this is a polar tangent line, you're first going to have to find the derivative of y over the derivative of x. Now, keep in mind that you're not just taking y over x and finding the derivative of that. No, you're just taking the derivative of the numerator and setting it over the derivative of the denominator. And so that's how you find the slope of a polar curve, or that's how you find the derivative of a polar curve. At which point you're going to have to plug in your theta or your r, depending on what variable you were given. From there, you'll be able to find your slope very easily, which will be your m. However, you're still going to have your initial coordinate in terms of r and theta. So you're going to have to convert this into x and y coordinates, or I should say a and b, which are x and y coordinates, at the point at which you're trying to find the tangent line. But again, it's quite simple to just translate those into parametric form. You just plug them in. So that's essentially how you find a polar tangent line, similar to all other tangent lines. Okay, this is practice problem 1. The first thing you may notice is that we are not actually given a polar coordinate point. Instead, we're just given our theta value at which we're trying to find our tangent line. That's okay, because with the theta value, we can find our polar, or our r value as well. And so it's not really a cause for concern. One thing I do want to modify, well, in fact, two things. I'm going to change this equation to r equals 3 cosine theta plus 1. And I'm going to change the theta value at which we find it to theta equals pi over 4. So if you feel confident with polar curves, or I should say polar tangent lines, then feel free to pause the video. If not, or if you want to check it, I'm going to go over it right now. So in order to find a polar tangent line, we're going to need the point at which we're trying to find our tangent line and the slope of the tangent line at that point. We're going to begin by finding the slope, and then later we can find the points. In order to find the slope, we're going to need to find dr d theta, also represented as dy d theta over dx d theta. In order to find both of those two derivatives, we're going to need x and y. So recall that the general equation or conversion equation, I suppose you could call it, for x is r cosine theta, whereas for y it's r sine theta. Now, from here, all we have to do is substitute our equation for r into our variable r in our general formula for x. And so we're going to do that. We end up with 3 cosine squared theta plus cosine theta. As I just said, I substituted r in for r, and then I distributed the cosine, and so that's how we ended up with this right here. So that's our x. That's our equation for our x value given the polar curve. From here, we need to find the y. And so we're going to use the same process, and we're going to distribute sine theta rather than cosine theta. And so this is equal to 3 cosine theta sine theta plus sine theta. Okay, from here we're going to find, well, we need to find both dy d theta and dx d theta. Let's start off with dx d theta. And dx d theta, as you could probably imagine, is the derivative of x with respect to theta. So I'll write that here. It's not really necessary, but whatever. And we're going to substitute our equation in for x. And so we're just going to find the derivative of the equation for x, which is going to be, I believe, -6 cosine theta sine theta minus sine theta. And now we can find dy d theta, which is just the derivative of y with respect to x, as you can probably imagine. This is going to be a bit difficult. So we can say that this is equal to -3 cosine squared theta plus 3 sine squared theta plus cosine theta. Okay, so we have from here our dx d theta as well as our dy d theta. Now we just need to find our dr d theta. And so I'll write that down here. And as I said multiple times, this can be represented as dy d theta over dx d theta. So we're just going to substitute both of our variables in, dx d theta, dy d theta. So let's do that right now. It's possible this can be simplified. I have no idea. And honestly, I don't really want to find out. So we're just going to write them as they are. Dy d theta is -3 cosine squared theta plus 3 sine theta sine squared theta plus cosine theta. And our dx d theta, which in this case is going to be the denominator, as well as like every other case, we're going to end up with -6 cosine theta sine theta. Oh, hold on. Sine theta minus sine theta. Okay, and so from now we have our dr d theta, and we're going to need to find the value when theta is equal to pi over 4, because that's the point at which we're trying to find the slope. Okay, so we just need to find this at the point when, as I just said, theta is equal to pi over 4. Now, you should have a basic understanding of your unit formula at this point, and you should know that cosine pi over 4 is equal to √2/2, and sine pi over 4 is equal to √2/2. Don't be concerned about not knowing the unit formula. I mean, you have to know it, but it's very methodical and predictable, so it's not really a pain. So I'm just trying this error because I don't have any room left. We just need to plug in our theta pi over 4 at every point. So, okay, I guess we got to do that then. -3 cosine squared pi over 4 is equal to -3 times √2/2 squared. Because if we consider that, I might as well just write this over here. cosine of 4 is equal to root 2 over 2. Sine over 4 is also equal to root 2 over 2. So just keep that in mind. So if we were to plug in pi over 4 for negative 3 cosine squared theta, what we're going to do is we're going to multiply our product here or by itself and then multiply it by negative 3. And in that scenario, we're going to end up with negative 3 over 2, because if we were to square this, we'd end up with 2 over 4, which is 1 over 2, times negative 3. So that's how we end up with negative 3 over 2. And we're going to do the same thing again. And we'll cancel that out later. And why I added this is because I just substituted pi over 4 in for theta for this term over here. And because the two are the same, as in cosine pi over 4 and sine pi over 4, they're going to cancel out as they have opposite signs. Okay, so then we're going to write the final term in the numerator, which is just going to be root 2 over 2. Okay, now we're getting to the denominator, which is going to be negative 6 times 1/2. Now this is because cosine pi over 4, sine over pi over 4, they're the same. We multiply them, we're practically squaring them. And so that's how we end up with that. Minus root 2 over 2. And so we're going to simplify at this point. So we're almost done, I guess. We can cross these two out. They combine to equal 0. So we're left with pi over 2 over 2 over negative 3, which I'm going to write as negative 6 minus root 2 over 2. Okay, and we can cross out these numerators and denominators. And so we end up with pi over 2 over negative 6 minus pi over 2. Okay, I'm really running out of room at this point, but I'm going to try to fit it all in. We have our slope. Now we just need our x and our y coordinate. We can do so by plugging in pi over 4 for x and pi over 4 for y. So I'm going to try to squeeze that in. X of pi over 4 is equal to negative 3 cosine squared pi over 4, which, as I think we've gone over, is equal to 3 over 2 plus root 2 over 2. Y, I'll write this in another color. Yellow's fine. Y of pi over 4 is equal to negative 3 times cosine of pi over 4 times sine of pi over 4 plus sine of pi over 4. And so we end up with 3 over 2 plus root 2 over 2. Okay, so at this point we are almost done. We have our x coordinate, our y coordinate, and our slope. I'm not lying this time when I say we're almost done. So our final answer, as in our actual tangent line, is going to be y minus 3 over 2 plus pi over 2, or sorry, plus root 2 over 2. And that happens to be equal to our slope, which is root 2 over negative 6 minus the square root of 2 times x minus 3 over 2. Oops, hold on. Plus root 2 over 2. And so that is our polar tangent line. This can, of course, be simplified. However, not only have I run out of space, I'm also too lazy to do it. So that's it for this question. Now time to move on to the second one. Okay, this is practice problem 2. Just like the last, I'm going to change the point at which, or the value of theta at which we find our tangent line. We'll change it to pi over 3. That's it. Actually, pi over 6. I prefer 6 over 3. It's even. Okay. We're going to employ the same process as the last. You're probably saying, like, what? This second practice problem isn't necessary, and you're right. But we're going to do it anyways. So x is equal to r cosine theta y is equal to r sine theta. We're going to plug in our values of r. So we're going to end up with 3 cosine theta plus 2 sine theta times cosine theta. That's our x coordinate. Our y coordinate is going to, or that's our equation for x. Our equation for y is going to be 3 sine theta plus 2 sine squared theta. Okay. At this point, we're going to have to find, sorry, I'm choosing a good color for this. We're going to have to find dx d theta as well as dy d theta. Which at this point you should know is both are equal to the derivatives of x with respect to theta and y with respect to theta respectively. So dx d theta, as I just said, it's the derivative of x with respect to theta. It's going to be -3 sine theta plus, okay, hold on, -2 sine squared theta plus 2 cosine squared theta. Now our derivative of y with respect to x is going to be equal to 3 cosine theta plus 4 cosine theta sine theta. Okay. We're going to, of course, model this as dr d theta. So we're going to put dy d theta over dx d theta, which I'm just going to simplify and say that's dy dx. And this is equal to 3 cosine theta plus 4 cosine theta sine theta. Should have done this in another color. Over -3 sine theta minus 2 sine squared theta plus 2 cosine squared theta. Okay. So from here, we can just actually simplify this a bit, if you'll give me a second. Okay, we need to find this at theta equals pi over 6. I'm going to write the values of both sine pi over 6 and cosine pi over 6 near the top, just so you can reference them when we're, if you're writing along with me, and also to make this more digestible. So cosine of pi over 6 is equal to √3 over 2. And sine of pi over 6 is equal to 1 over 2. So keep that in mind. It'll make it a lot easier. It'll make my explanation a lot easier because I don't really feel like referencing back all that much. So now we just have to find dy d theta over dx d theta at point theta equals pi over 6. And so we're going to do that. I'll just say it's up here. Okay, so 3 cosine theta, that is going to be 3 over 2 √3. God, okay. Plus 4. Sorry, no. Plus √3. Over -3 over 2 minus 1/2 plus 3 over 2. Okay, that actually wasn't that bad. Now, can you simplify this further? Absolutely. However, I don't really want to. So, I mean, okay, fine, I'll do it a bit. We can rewrite this denominator. I'm actually just checking to see if I've gotten everything correct. I'm just stalling. I am filibustering, you might say. Okay. We can simplify this denominator. In fact, we'll just simplify the whole fraction as √3 over 2 plus √3. Now, I don't like fractions and quotients within fractions and quotients, but I also am not going to fix it. So actually, you know what, I will. Okay, sorry this is taking so long. This is actually equal to 3 root 3 plus 2 root 3, which we can rewrite as 5 root 3. And so I believe that is our slope. If that is incorrect, you just correct me in the comments, and I'll re-upload this video. So at this point, we have our slope for a tangent line at point pi equals 6. From here on out, we just need to find the value of x at pi over 6 and the value of y at pi over 6. And then from there, we can plug all three unknown variables into our standard formula equation to get the polar tangent line. So I'm running out of colors actually. I'm going to write our x at pi over 6. And that is equal to 3 cosine pi over 6 plus 2 cosine pi over 6 times sine pi over 6. And that's just because I'm substituting pi over 6 in for our formula for our equation for x. So this is equal to 3 root 3 over 2 plus plus root 3 over 2. From here, we just need to find y of pi over 6. And naturally, as you could presume, we're just going to input pi over 6. We're going to put pi over 6 in place of theta. And so we end up with 3 over 2 plus 1 over 2. And we can just simplify this as 2. And so I'll do that right now. Now this equation, since it just happens to be a lot simpler, as you can probably tell. Both our slope and our y-coordinate are both just one term. And that occasionally happens. Sometimes polar tangent lines can be a pain. However, you still got to do them. So as they appear on the calculus AP/BC exam. I forgot to mention that earlier. This is not seen in calculus AB. So if you've made it this far and you're in AB, I apologize. Also, this does have a negative sign. Okay, so our standard form is, of course, y minus a being the y-coordinate which we're trying to solve, or which we're kind of trying to find the tangent line, times m x minus b. B, as you could probably presume or assume, is the x-coordinate which we're trying to find our slope or our tangent line. Y is going to be equal, or a is going to be equal to 2. M is going to be equal to negative 5 root 3 times x minus root 3 times 3 over 2 minus root 3 over 2. And so that is our tangent line for the polar curve 3 plus 2 sine theta equals r at point theta equals pi over 6. I hope you enjoyed this video. I've taken quite a furlough from making calculus tutorials. I plan on uploading much more frequently. It's just that school started again, and so I'm kind of a bit short for time. But I hope you enjoyed this video. If you did, please leave a like, and please consider putting a comment in the comment section for any future videos that you suggest or you would like to make, or you would like to see me explain. Thank you.